first thing you need to understand is electrolytes and no-electrolytes. So non-electrolytes are those compounds, or you can say substances, which do not conduct electricity. And the reason they do not conduct electricity is they do not dissociate into their ions. Examples are glucose or any other sugar, gaseous hydrocarbon, for example methane, SF6, etc. While electrolytes are those which conduct electricity, they dissociate into their ion. And you have already studied that the conduction of electricity by a solution is because the compound is present in the ion form, and those ions help in the transportation of electricity. So examples are NaCl. It dissociates into Na plus and Cl negative, HCl, H positive, Cl negative, H2SO4, 2H positive, SO4, 2 negative, NaOH, Na positive, OH negative, acetic acid, CH3CO negative plus H positive. And the dissociation happens this way. If you take a journal ionic compound, it will dissociate in such a way that the numbering here, smaller alphabet, they will come as stoichiometric coefficients, and they will get a charge in such a way that these charges neutralize each other. If you see here, we have A times V positive. So the positive charge is AB positive. And if we see here negative charge, it is B times A negative. So in short, these charges cancel out each other. Alright, so you are getting a neutral compound. Now electrolytes are also of two types, strong and weak electrolytes. Strong electrolytes are those which completely ionize. Once you form the aqueous solution, they completely ionize into their ions, HCl and NaOH. While weak electrolytes, they do not dissociate completely. They will be partially dissociated. For example, if you make an aqueous solution of acetic acid, you will have three species in the water. Your acetic acid, your CH3CO negative, and your H positive. These three species will be present in the solution, and there will be an equilibrium between acetic acid and these two species. While if you consider HCl and NaOH, these will completely dissociate. There will be no equilibrium between these species. Like there will be no HCl molecule present in the aqueous solution, only H positive and Cl negative. So the ionic equilibrium has its significance only in the case of weak electrolytes. Only weak electrolytes show ionic equilibrium. Alright. The next topic that you have to study in ionic equilibrium is theories of acids and bases. So there have been three theories that has been proposed for acids and bases. First is Arrhenius theory, second Bronsted lowry theory, third Lewis theory. So what Arrhenius suggested was the acids and bases are those species which provide H positive and OH negative respectively when an aqueous solution is being formed. Or you can say that an acid is a substance which dissociates in water to provide H positive, while a base is a substance which dissociates in water to produce OH negative. Examples are nitric acid. Nitric acid, when forms an aqueous solution, it provides two ions, H positive and NO3 negative. Since it is providing H positive, so it is an acid. Another example, you take NaOH. When it dissociates, it provides Na positive and OH negative. Since it's an OH negative provider, so it's in base. It's a base. Alright. But there are some limitations with Arrhenius theory. It doesn't explain the basicity of compounds like ammonia. Ammonia is neither a proton donor nor an OH negative donor. But all of us know that ammonia is a base, but Arrhenius theory doesn't explain this. So it's the limitation of Arrhenius theory. Next comes Bronsted lowry theory. This suggests that a proton donor. This theory is completely based on proton. If the species is proton donor, then it's an acid. If it's a proton acceptor, then it's a base. Let's take a general reaction. HA is a substance. When an aqueous solution is being formed, it provides A negative and H3O positive. Now what Bronsted lowry said, an acid-base reaction is acceptance and release of proton. So what is happening? It's an acid. It donates its proton to H2O. So it's an acid and water is acting as a base here. Alright. For example, if you take the acetic acid example, acetic acid on forming an aqueous solution, or you can say on reacting with water, forms CH3CO negative and H3O positive. So here CH3COH is a proton donor and water is proton acceptor. So it's an acid and this is a base. Alright. Another example, you take ammonia. Arrhenius theory could not explain ammonia's basicity, but if you take Bronsted lowry theory, ammonia on reaction with water gives us NH4 positive and OH negative. So what is happening here? Ammonia is accepting a proton, so it's acting as a base. And if you see how water is acting as an acid, because it is providing water. Now why I am writing about water here? If you see the previous example, water is acting as a base, while in the case of ammonia it is acting as an acid. So water is an ampholyte. Ampholyte are those species which can either accept a proton or donate a proton. So that kind of behavior is called amphoprotic behavior. This protic is for proton. Alright. So it shows amphoprotic behavior. Another example is HSO4 negative. If you make an take an aqueous solution, what happens? Your sulfuric acid dissociates to form HSO4 negative. This further dissociates into SO4 negative and proton. So this species is ampholyte. It can either go to the direction where sulfuric acid is being formed, or it can go to the direction where SHO4 negative is being formed. So this species can act as an acid as well as base. So it's another example of an ampholyte. Another thing that Bronsted lowry suggested was concept of conjugate base and acids. Alright. So on the reactant side we have already discussed what is acid and what is base. But on the other side also, if you see, it has given a term as conjugate acid. This is conjugate acid, this is conjugate base. Alright. And there is a relation between the acidity of conjugate acid and your reacting acid. For example, if you compare the acidity of your acetic acid and HCl, all of you know HCl is more acidic as compared to your acetic acid. But if you take its conjugate, it will be Cl negative and CH3CO negative. The relation will be reversed. Your acetic acid will have higher tendency to form acetic acid as compared to Cl negative. That means the tendency to accept the proton will be higher in case of CH3CO negative as compared to Cl negative. So you can say the basicity of conjugate acid of acetic acid is higher as compared to that of HCl. So the relation is reversed. Now third theory is Lewis theory. Lewis suggested that an acid is an electron pair acceptor while a base is an electron pair donor. Alright, so let's say if you make the Lewis structure of OH negative, so what happens? This OH negative donates an electron pair in order to form a bond with proton and to form a water molecule. So here the donor is base while the acceptor is acid. Alright, this is Lewis acid, this is Lewis base. Another example is ammonia. Again, Arrhenius could not explain it there. So let's see whether this Lewis theory can explain or not. If you write the Lewis structure of ammonia, you can see the ammonia, the nitrogen atom have a lone pair. This lone pair will form a bond with proton and form NH4 positive having a structure like this. Similarly, BF3 is an electron deficit species. So it acts as an electron acceptor, and when ammonia donates a lone pair from nitrogen to boron, it forms a bond like this. So these are the three theories of acids and bases that we were supposed to study in